KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we will discuss about gravitational potential energy. Okay, right? It is what 8th class from gravitation chapter ma. But anyhow, in this class our interest is to discuss about gravitational potential energy. Gravitational potential energy. Okay, right? But in our previous chapter, that is what work power energy, there we had a discussion about potential energy. So potential means which indicates position, right? So the energy possessed by a body due to its position, because the body need not to be at one particular place. For example, if you see the entire universe, if you see the planet Earth, which is a part of universe, you know, the body may be at the center of the earth, the body may be on the surface of earth, the body may be at certain height from surface of earth. So whatever it may be, what I am saying is, the position of the body may not be fixed, need not to be fixed. So the energy possessed by a body due to its position, I am not taking internal forces into account here. Just I am talking about the position of a body, where it is. Is it on surface of earth? Is it at the center of earth? Or is it at certain distance from surface of earth? These are all things which accounts to calculate the potential energy. Even I didn't enter into the gravitational potential energy. Still I am in a discussion, I am explaining what is the potential energy, right? So what I am concluding regarding the term potential energy is the energy possessed by a body due to its virtual position. Why I am saying virtual position? The position need not to be fixed. The position may change with respect to time, with respect to surroundings. That's what indicating potential energy is the energy possessed by a body due to its position. Due to its position. Okay, right. But potential energy not only because of gravitational force, because of elastic force. That is what potential energy stored in a spring. Potential energy stored in a spring. That's why there are different things. Based on that, the body is going to gain, the body is going to possess potential energy. But in this class, in this chapter, our discussion is limited to the gravitational potential energy. Gravitational potential energy. Okay, right. So according to Newton's law of universal gravitation, every two bodies in this universe attracts with certain amount of force. That force is directly proportional to the product of their masses, I mean masses of the bodies, and inversely proportional to the square of the distance between their center of masses. Square of the distance between their center of masses. Okay, right. That is what Newton's law of universal gravitation. Okay. Here, if you take Earth as a unit, you know, Earth is going to attract the bodies towards its center, including us. Though we are living being, but we are going to attract by the earth a certain amount of force towards its center. That's what you can calculate by using the formula F is equal to capital G into m by r square. Okay, see here. We had discussed earlier the notion of potential energy as being the energy stored in the body at its given position. Okay, right. If the position of the particle changes on account of forces acting on it, this is what because of external force. The external force may be any, either it may be a that is what elastic force, either it may be a gravitational force, whatever it may be the reason. But what he is saying is, if the position of the particle changes on account of forces acting on it, on account of forces acting on it, then the change in its potential energy is just, then the change in its potential energy is just the amount of work done on the body by the force, okay. So what he is saying, then the change in its potential energy is just the amount of work done on the body by the force. For example, imagine an object here, suppose some force is coming, right, some force is going to apply on the body, some force is coming means we are going to apply certain amount of force on the body to change its position from here to somewhere. If you observe carefully, there will be a change in potential energy in this situation, but what is the cause for change in potential energy? Change in position. And what is the basic cause for change in position? The applying of external force, application of external force, okay, right. That is what he is saying here. Observe carefully. If the position of the particle changes on account of forces acting on it, then the change in its potential energy is just the amount of work done on the body, is just the amount of work done on the body, just amount of work done on the body by the force, full stop. As we had discussed earlier, forces for which the work done is independent of the path are the conservative forces. So in the chapter of work power energy, we had a discussion about conservative forces and non-conservative forces. I'll tell you a little bit about conservative forces and non-conservative forces. The force due to which, okay, otherwise you can say like this, the work done due to which type of force, the work done due to what type of force and what force, the work done due to which force, path dependent, then that force is said to be non-conservative force, non-conservative force. For example, frictional force. Next, in another aspect, the work done due to which force is path independent. Observe carefully, there is a small difference. The work done due to which force is path dependent. That force is called as non-conservative force. For example, frictional force. Next, the work done due to which force is path independent or position dependent. That force is called as conservative force. For example, gravitational force. The best example of conservative force is gravitational force. Okay, right. This is what we already discussed in the chapter of work power energy. Next paragraph. See here. The force of gravity is a conservative force, and we can calculate. The force of gravity is a conservative force, and we can calculate the potential energy of a body arising out of this force called the gravitational potential energy. So the new term here, that is what gravitational potential, because till now we focused on potential energy, but here he is saying that gravitational potential. So what is the gravitational potential energy? The force of gravity is a conservative force, right? That's we know. We can calculate the potential energy of a body. We can calculate the potential energy of a body arising out of this force, called the gravitational potential energy, right? Full stop. Next, consider points close to the surface of Earth. At distances from the surface much smaller than the radius of the earth. In such cases, the force of gravity is practically a constant equal to mg directed towards the center of the earth. Once again you listen ma. Consider points close to the surface of earth at distances from the surface much smaller than the radius of earth. So what is the radius of earth? 6,400 kilometers. 6,400 kilometers. If you take out a point from surface of earth, for example, at 10 kilometers, at 5 kilometers, at 1 kilometers, otherwise at 500 meters. So these are the points which are close to the surface of earth when compared to the radius of the earth. In such cases, the force of gravity is practically a constant. In such cases, the force of gravity is practically a constant equal to mg. So m is the mass of object and small g is the acceleration due to gravity. So whatever the object, that is not matter here, but small m is the mass of the object, which is going to based on that we are going to calculate the gravitational force. Next, what is the direction of this mg? Because force is a vector quantity, no? So which has both magnitude and direction. So this is the direction of this mg is towards the center of earth, right? So equal to mg directed towards the center of earth, okay, right, full stop. If we consider a point at a height h1 from surface of earth and another point vertically above it, if we consider a point at a height h1 from surface of earth and another point vertically above it at a height h2 from surface of earth. For example, if it is the earth, so this is like h1 and it is like h2. You just imagine yourself, this is the earth means it is like h1 and it is like h2, okay, right, see this. So the see here if we consider a point at a height h1 from surface of earth and another point vertically above it at a height h2 from surface of earth, here the work done in lifting the particle, that is what the work done in lifting the particle of mass small m, this is what comma, not full stop, it is a comma. The work done in lifting the particle of small mass m from the first to the second position is denoted by, W12, because it is going from 1 to 2, no, h1 to h2, right. So W12 is equal to force into displacement, that is equal to mg into h2 minus h1. What is the displacement? h2 minus h1, no. So here the formula for work done is force into displacement. So force is mg, displacement is h2 minus h1, okay, right. It is like equation number 8.21 according to our textbook. This is the equation of number 8.21. 8 is the name of the chapter and 21 is the equation number from this chapter, from starting of this chapter, from introduction of this chapter, right. W12 is equal to force into displacement, that is equal to mg into h2 minus h1. Next, if we associate a potential energy W of h, that is what work is a height means that is what position. If we associate a potential energy at a point at a height h above the surface such that W is equal to mgh plus W naught, where W naught is a constant, then it is clear that W12 is equal to W of h2 minus W of h1. It is like equation number 8.22. Now, the work done in moving the particle is just the difference of potential energy between its final and initial positions. The work done in moving the particle is just the difference of potential energy between its final and initial positions, full stop. Observe that the constant W naught cancels out in equation 8.22, setting H is equal to 0. Setting H is equal to 0 in the last section, where W is equal to W naught. H is equal to 0 means what, no? H is equal to 0 means the point on surface of earth, no? The points on surface of earth. Thus, W naught is the potential energy on the surface of earth. W naught is the potential energy on the surface of earth. Full stop. Next, in continuation to that, that is here next paragraph. If we consider points at arbitrary distance, if we consider points at arbitrary distance, points at arbitrary distance from the surface of earth, the result just derived is not valid. The result just derived is not valid, since the assumption that the gravitational force mg, what we thought, what we calculated, is a constant and is no longer valid. And is no longer valid. Here he is talking about the validity. Just focus. If we consider points at arbitrary distance from the surface of the earth, the result just derived is not valid, since the assumption that the gravitational force mg is a constant is no longer valid. Okay. However, whatever the discussion we had, however, from our discussion, we know that a point outside the earth, the force of gravitation on a particle directed towards the center of the earth. That is what we can calculate from the formula of Newton's law of universal gravitation, that is F is equal to, right? F is equal to capital F. Capital F is equal to capital G into capital M E. E means earth into small m is the mass of the object, divided by r square is the distance between the center of the earth and the center of mass of the object. This is equation 8.23. Okay. So this is the formula for gravitational force between the body and the earth. Next, if we now calculate the work done in lifting a particle. Now if you calculate the amount of work done in particle, so there W12 is equal to integration r1 to r2 gmm by r square into dr. That's the formula, integration 1 by x square dx formula, So that you apply here, that is integration 1 by r square. These are all constants, we are taking out gmm into, if you apply that formula and apply the limits, then you are getting W12 is equal to minus gme into m small m into 1 by r2 minus 1 by r1. That is 8.24, equation number 8.24. Right, in place of equation 8.21, that is where, this is what 8.21. In place of equation 8.21, you can write W of as a function of r distance is equal to minus gme m by small r plus W1. Here r small r is greater than capital R, so that is what is the radius of earth, and it is the distance of the particle from center of earth. So that once again W12 is equal to W of R2 minus W of R1. Setting R is equal to infinity. Setting R is equal to infinity in the last equation, we get W is equal to W1. He is asking to put R is equal to infinity. You know very well, something by infinity is 0, no? So this term will become 0 when you put R is equal to infinity. Then W will become equal to W1. Thus, W1 is the potential energy at infinity. W1 is the potential energy at infinity. One should note that only the difference of potential energy between 2 points has a definite meaning from equation 8.22. From equation 8.22 and equation 8.24. So from these two equations, there is a meaning only the difference of potential energy between 2 points, right? That only he is saying. Now, one conventionally says W1 equal to 0, one conventionally sets W1 equal to 0. W1 equal to 0, so that the potential energy at point is just the amount of work done. W1 equal to 0, so that the potential energy at point is just the amount of work done in displacing the particle from infinity to that point. I will repeat once again because of this point is important. One conventionally sets W1 equal to 0, so that the potential energy at point is just the amount of work done in displacing the particle from infinity to that point. In displacing the particle from infinity to that point. Okay, right. Next, we have calculated the potential energy at a point of a particle due to the gravitational forces on it due to the earth, and it is proportional to the mass of the particle. It is proportional to the mass of the particle, full stop. The gravitational potential due to the gravitational force, the gravitational potential due to the gravitational force of the earth is defined as, I will repeat once again. See here, we have calculated the potential energy at a point of a particle due to gravitational forces on it due to the earth, and it is proportional to the mass of the particle. Is proportional to the mass of the particle, right? Okay, here is the equation, and here you can see this is what suppose if you take one mass as a mass of earth, another one is the mass of the particle, then gravitational potential is directly proportional to the mass of the object. No, that only he is saying here. So what he is saying means, we have calculated the potential energy at a point of a particle due to gravitational forces on it due to the earth, and it is proportional to the mass of the particle, full stop. The gravitational potential due to the gravitational force of the earth is defined as the potential energy of a particle of unit mass at that point. The gravitational potential due to the gravitational force of the earth is defined as the potential energy of a particle of unit mass. Potential energy of a particle of unit mass at that point, full stop. From the earlier discussion, we learned that the gravitational potential energy associated with the particles of masses small m1 and small m2 separated by distance small r is given by v is equal to minus g into m1 m2 by r. If we choose v is equal 0 as r tends to infinity, suppose if r is infinity means what is v? V is 0, no, because something by 0 is infinity. Okay, right. Now here a small thing, I didn't write here but I am saying, please be concentrate. It should be noted that an isolated system of particles will have the total potential energy that equals the sum of the energies for all possible pairs of its constituent particles. I'll repeat once again. It should be noted that an isolated system of particles will have the total potential energy that equals the sum of energies given by the above equation. This is what the equation. Sum of the energies for all possible pairs of its constituent particles. This is an example of application of superposition principle. Okay. So what he is saying at last, this is only for two particle system. No, this is the gravitational potential energy only for two particle system. Suppose if you want, you can extend this for n particles but different pairs. For example, it is one pair, 1 2. You can take 3 4. You can take 2 3. You can take 4 5. Like that it goes on. Okay. So in this class we discussed about gravitational potential energy. Okay. What is potential energy? Already we came to know from the chapter of work power energy, but here in this class our discussion is gravitational potential energy. Okay, right. Here by taking the body, from surface of Earth at h1 height and h2 height. This is the equation. And then that is what the amount of work done on surface of Earth is like W naught. That's why he has written. And then it is clear that from these two equations he is writing W12 is equal to W of h2 minus W of h1 from this equation and this equation. After that, is the expression for gravitational force. And then we are clearly writing the amount of work done in lifting a particle. Right? That is what from one position to another position, right? I already told you, this is what mass of Earth, and this is the mass of the particle, and r is its distance from the center of Earth. Okay. So if we now calculate the amount of work done in lifting a particle from r is equal to r1 to r is equal to r2, small r is equal to r1 to small r is equal to r2, that is what r2 is greater than r1 r2 is greater than r1 along a vertical path, then we are getting this equation. That is what here I have written now. That's it. Okay, right. Afterwards it is that is what he is taking about the possibilities of W1, and then here he is saying about the gravitational potential energy, and finally we got a mathematical relation for gravitational potential energy, that is V is equal to minus G into m1 m2 by small r. Okay, right. So in our next class we will continue with next continuation topic. Okay, thank you.